This is Thursday, 10th of March 2022. Okay, so what are we going to do today? What are we going to do right now? We're still looking at the electric potential, okay? So we're going to find, find the electric potential of a cylindrical charge, of a uniform cylindrical charge distribution. Okay, why are you doing that? Okay, there's a reason why we're doing that. We're going to do that. Because we did an experiment on that. And I want you to compare, the regression equation you got with the theoretical result we are going to obtain here. We are going to obtain here. Okay? What? Yeah, lab 2. We're going to do that because we did an experiment. Here you go, lab 2. Okay? So consider uniformly charged cylinder, uniformly charged cylinder of charge density rho and radius r. Okay, we're not gonna do for r less than r, big R, and I need more here. Cylindrical, I need the other result, not this one. This one is linear with r. So let's go back here. Cylinder. Long uniformly charged cylinder. Okay, here you go. I didn't do for, strange. It looks like I have to do that. I didn't do for R bigger than big, small r bigger than bigger r. Okay, so I have to do that. Let's calculate the electric field, and then, yeah, that's for r less than big R. Let's do for r greater than big R. Okay. Unfortunately, I didn't do that for the solid cylinder, so I'm going to do that right now. Okay. So here you go. Q enclosed, okay, would be rho v divided by epsilon naught, and the volume in this case is the volume of the cylinder. So instead of lowercase r, we are going to use uppercase R and the L on the right side. Okay. Remember that what we did in the experiment, we measured only the electric potential between the outer surface of the inner electrode and the inner surface of the outer electrode, right? So all you have to worry is about R greater than big R. You don't have to worry about the bulk of the cylinder. Let's calculate the electric field first, and after calculating the electric field, we find the electric potential. Okay? So here we go. We get E dot dA here is going to be 3 surfaces. 1, 2, 3, right? This going to go right in here. 3 surfaces. The contribution of the other 2 surfaces are the cap of the cylinder, and the electric field has a radial direction which is perpendicular to the area vector of those 2 caps. That's why we have this 0, those 2 zeros right in here. And what's next? Okay, we got the electric field on the surrounding the cylindrical surface is constant. The magnitude of the electric field is constant, not the direction, of course. So because of that, it can be taken out of the integral. And now we use the area of the Gaussian surface. This is the area of the Gaussian surface. On the left side is the is an integral of the Gaussian surface. On the right side must be the electric charge that is in the cylinder. Okay? So we can finish our calculations here. And let's see. That's the one we are gonna use right now. I'm going to cancel out the pi and the L. Pi and L. Okay, and then we solve for, and that's what we get. Over 2r. Okay, rho r squared over 2r. Just like in the case of the linear charge distribution, the electric field decreases with the inverse of the distance. Goes down with the inverse of the distance. Okay? If we are going to here write that in vector format, we can do that. And now I'm going to drop this one subscript because we don't need that anymore. Oops. And I'm going to, interesting. Okay, hat R. Oops, he doesn't like it. Interesting. How do you do that? Huh. He doesn't put the hat there, huh? Interesting. Let me see if it's gonna put that now. Yeah. Huh. Okay, I gotta check why is that. The keystrokes are much quicker than using this pad here. Here you go. So that's if the cylinder has positive charges, then the electric field is away from the cylinder. If the cylinder has negative charges, right here in the charge density, the electric field is towards the center. Okay? So how do we, now we're going to calculate. Now we're going to use the above result to determine the we're going to use the above result to determine the electric potential of the cylinder. Okay, so let's go ahead and get the definition of electric potential. Let's go back to the definition. It's okay to keep on checking the definitions, okay, every now and then, but eventually you have to memorize. There's a relationship between the electric potential and the electric field, okay. So there are two ways of solving for the electric potential. Okay, here you go. That's how, remember, two ways of solving for the electric potential. Either using Coulomb's law for the electric potential or the integral that you see right in here, right? So here you go. I'm going, oh, what's that? Okay, I put it in the wrong place. Yeah, the wrong place. It goes right in here. Put the electric field right inside this integral, and then go ahead, do the dot product, right? We are talking about uniform charge distributions, and so we can take out everything that's constant from inside the integral and put outside. And the only thing that's left is 1 over r. And then when we do the r dot ds, don't forget this r here is the polar coordinate, okay? It's the polar coordinate. So when we do the r dot ds, it becomes dr. The polar coordinate, not the radial direction in the spherical coordinate. We have here, and now we can go ahead and do this integral that is going to be the natural log of r. Okay. In this specific case, r is always positive, and we can apply the limits brackets and separators. Apply the limits right in here. Okay, that's going to be this one R naught. I'm gonna put here R naught to RF. Well, I'll put instead of RF, I'm gonna use R. Here we go. RF, and we go ahead and use this result. We do not need okay, so let's not forget that delta V is V minus V naught. Okay, I put it like that. And then we have our result for the electric potential. Okay? So here we go. Do you remember that I asked you to fit a curve in terms of log, right? That's exactly what I did here, right? Let me see if I can write that. Yeah, leave this way. So, the log. That's why you got the best fit for the log, because the theory notes. Here you go. We'll write that down here for it. Notes that the theory predicts that the electric potential varies with the log of the distance, of the polar coordinate, of the radial distance. Okay, which was the best fit we got for the experiment. Okay, that oh, that's what we can say here. Now, what we are going to do now is going to the next chapter. Go back here to the next chapter, and that's going to be capacitance and dielectrics, chapter 26. Okay. Now we will cover chapter 26, capacitors and dielectrics. Okay, so remember what I told you, right? In the lab, there are 4 basic devices in electricity and electronics. The simple of them, here you go, and they are what? Capacitors, resistors, inductors, and transistors. The simplest of them is this one that you see right in here. Capacitors is the simplest of them. Capacitors are the simplest of them. Let me show you how capacitors look like. How capacitors are, and we have all sorts of capacitors out there, by the way. Remember, there's a reason why we study those things, right? We study those things because those devices really exist and they are important. Oh boy, it looks like the cloud is low now. Let me see if I can get out of this place here. Oh gosh. Let me pause my... Yeah, why is it doing that? Oh gosh. It was not doing that before, right? Why is it doing it now? So chapter 26, dielectric capacitors and dielectrics. So there are, that's when, looks like he didn't like me when I do the paragraph, I guess. Let me see. Paragraph. This one. Okay, here you go. Okay, capacitors and dielectrics, okay? Remember that there are 4 basic devices in electricity and electricity magnetism and electronics and electronics. They are capacitor, the resistor, the inductor, and the transistor. Okay, the capacitor is the simplest of them. The capacitor is the simplest of them. And let's see how a capacitor looks like. The most generic capacitor. How does the most generic capacitor looks like? Huh? PowerPoint, let's go there. Here you go. This one. The most generic capacitor looks like something like that. Go, capacitor. Yeah, go. The most generic capacitor is just two pieces of metal. That's what it is. Okay? I can get one piece of metal and another piece of metal. I can put them at different distances, or depending on the piece of metal, you can put them, one surrounding the other, but never touching them. This line here means that you have a dielectric insulating this metal. The metal cannot be touching any other metal, okay? This this side here cannot be touching this other one. So, and it gotta be they usually do a conductor device. Let's see, I don't have two pieces of metal. Oh yeah, here you go. I have one here, another. So let's say, here you go. If this guy is electrically insulated, and this other also electrically insulated, we can say that those two metals can be a capacitor. Okay, that's the most generic way of defining a capacitor. But this capacitor that you see right in here is not charged, has no charge whatsoever. And because it's not charged, it's not useful at all. In order to make the capacitor useful, you have to somehow charge the capacitor. But one must have a positive charge and the other must have a negative charge. Okay, that's how you come up with a capacitor. And the amount of charge must be the same, just the opposite charges. When you get something like that, those two capacitors are going to be at different, are going to have a difference of potential. They're going to be held at two different potentials. This guy is going to be held at one potential. This other is going to be held at another potential. Okay? And like I said, this one is the most generic configuration of a capacitor. But you can have simpler configurations, like this one. The parallel plate capacitor, for instance. You can have a planar sheet negatively charged and another one positively charged. You already know how this type of charged metal plates behave. Okay? Let me see. Yeah, we can have a spherical capacitor. One smaller sphere surrounded by a larger sphere. Note that they have the same amount of charge, but with different signs. Okay? The positively charged sphere has an electric field that points towards the negative one. Okay, and if this guy here is a shell, a cylindrical, spherical shell, then the electric field here inside is going to be zero. Here too, the electric field on the outside of this capacitor is going to be zero as well. Spherical, and then we must have spherical. We can have either the positive charge on the outside, the negative on the inside, or the negative on the outside and the positive on the inside. And then you can have a cylindrical capacitor as well. Okay. What we did in the lab, in the second lab, was a cylindrical capacitor. Okay, the inner one was positively charged, remember? And the outer one was negatively charged. And we need this one too. We did this one as well, right? So what we did there, upstairs in the lab, was both a parallel plate capacitor and a cylindrical capacitor. So that's the configuration of those are specific configurations of a capacitor. So let's talk about that again. Again, here is one capacitor, the most generic capacitor. Any geometrical configuration, a metal charged, two pieces of metal charged. One with positive charge, the other is negative charge. They are separated and they are insulated of one another. They cannot be touching each other. The medium in between must be a dielectric medium. A dielectric medium does not conduct electric charges. However, if you put a conducting medium between those two metals, what's going to happen? The capacitor is going to become discharged. Okay? A specific capacitor configuration that you're going to find in the market, sold at electronic stores again, is the parallel plate capacitor, the spherical capacitor, and the cylindrical capacitor. Okay? Here are the dimensions of the cylindrical capacitor: inner radius A, outer radius B. Okay? So we can solve. We already solved for this type of the electric field for this type of configuration, right? This is not the parallel plate capacitor. Okay, so here you go. Let me show you some capacitors that are sold out there in the market. Okay, if you are not familiar with them, there are all sorts of capacitors. There are small capacitors and there are large capacitors. There are even microscopic capacitors. Google capacitors, Wikipedia. Capacitor Wikipedia. Here you go. We have a bunch of capacitors that are upstairs. I have capacitors that are at home too. So here you go. Here are all sorts of capacitors. This one seems to be a cylindrical capacitor. Again, those things are sold in the market. They vary in price anywhere between like a 10 cents all the way up to $20, $30. Okay, here's another cylindrical capacitor. These ones here seems to be a parallel plate capacitor. You cannot see the parallel plate capacitor because they wrap that up with some dielectric material. Okay, I don't see any spherical capacitor here. Okay, this one that you see here is using your tuning radio. Okay, and there are also spherical parallel plate capacitors. It's also parallel plate capacitor. Let's see. Let me see if you have another picture. Okay. Leyden jars. That was the first capacitor. Okay, here you go. That's another capacitor. We have something like that there upstairs. This is a parallel plate capacitor. Okay. Here is one plate. Here is the other. This the material in between the two plates is the air. Is a dielectric. Air is a dielectric. But you could put another dielectric there too. You could have put like a plastic or a piece of paper. Okay. This capacitor is kind of fancy because you can change the distances between the plates. Okay. Like I said, we have something like that there upstairs. I can show that to you. So here you go. The symbol of the capacitor is the symbol for the parallel plate capacitor. Let's see if I have it for you. Go. Oh yeah, here you go. See, we usually use this symbol here for the capacitor. Okay? And then there are some special types of capacitor that are called the polarized capacitor. Capacitors that has a polarization. We have some of those in there. And that's the symbol for a polarized capacitor. In the polarized capacitor, you must connect this plate here with the positive of your battery. And this one is the negative. This one is not polarized. Yeah. Yeah, go ahead. Yeah, that's right. And damage it. First damage, right? And then it explodes. I used to do those experiments in the lab, and I tell my students from the very beginning, this is a polarized capacitor. And the capacitor clearly shows which one is the negative and which one is the positive. And I tell my students, don't connect the negative side to the positive of the battery. And yet, most students comply. Most students comply, okay? But then there's one or another group that they connect the negative with the positive. They perform the experiment and the experiment doesn't work. Okay? So, and then when I go investigate what happened, that's because you didn't charge the capacitor properly. And you have this risk, right? You can explode the whole thing. Not only damage, but also exploded. Okay, and I suspect, when I do those experiments with capacitors, I usually get like a 30% difference, percentage difference. I suspect that because the capacitor was damaged in the past, and now we are not getting as good as percentage difference, you know. But that's what I usually get, 30%. Sometimes I get 10% or less, you know. But there are some capacitors out there that we do the experiment and we get like a 30% difference. And let me see if we have something else here. Yeah. Oh, and what about this capacitor here? This third one, this third symbol here. What does this arrow means? Do you have an idea what this arrow means? Here you go. See, that's a variable capacitor. It's a capacitor that you can change the properties of the device. Okay? So that picture, that fancy capacitor that you saw, that I showed to you, is a variable capacitor. Where is it? Yeah, this one right in here. This guy here is a variable capacitor. If you change the separation between the plates, you're going to vary the properties of this capacitor. So this is a variable capacitor. Okay? I'm going to do the following. I'm going to go upstairs and I'm going to get one of those capacitors that we have, okay? It's 534 right now. Yeah.